welcome to SMathHacks 2024. So what is SMathHacks? This is NCSSM's annual hackathon. We've been going this is our 5th year running, and it's basically just a weekend to make whatever you want, have fun, and eat some good food. Code, make, and present your way to success. As we said, we have 3 campuses per se. We have our Durham side here. On that screen over there, we have our Morganton campus. And we also have a few people joining us from across the entire state of North Carolina online. Who here has been to a hackathon before? And whose is this first hackathon? Okay, yeah, so we have a bunch of people who are very new to hackathons. And hackathons, what can I say? They're an amazing event for you to demonstrate and use your knowledge in CS. And even for people who've never coded before, there's so many opportunities. We're going to be, when we get to the schedule, I'll talk a bit more about that, but here's the schedule, right? So you can see those gray blocks on the screen. Those gray blocks are our workshops. We have guest speakers from many different businesses coming in to present and teach you about some really cool software and hopefully help you get coding yourself. So yeah, this has both Durham, Morganton, and virtual information. Right now, we are during the opening ceremony and the keynote. Immediately after this, we'll be doing team formation and breakfast. The schedule is a bit outdated for our virtual folks. There is a Zoom link on the schedule we sent out. You can join that. We'll place you in a breakout room. And in that breakout room, you can, I think I've lost tracking. Okay, there. In that breakout room, you can meet with other virtual people and form teams there, think of ideas. Immediately after our team formation breakfast, we'll have our first workshop. And this is your time to break out, start brainstorming ideas, start coding for the next 36 hours. We'll have lunch downstairs in Woolworth. In Morganton, it's going to be near the cafe area. And for virtual people, go downstairs, get some lunch with your family, I guess, or with your friends. Oh, let's go back one slide. Yeah. A few more workshops, and just for the rest of the day, I guess it's just work on your project. What's happening here? Okay. Yeah. So what's next? Tracks. This year, SMathHacks is an environmental hackathon. We are focusing on 4 main tracks: resource conservation, renewable energy, equal equality, and sustainability. Let me move this out of the way. Yeah, so there's more information on the website for each one of these tracks. You just go to smathhacks.ncssm.edu, and all of the information is right there for each of the hacks, for each of the tracks. You guys were not supposed to see this one. Okay, here are the prizes for SMathHacks. So let's see, what are the tracks? For resource conservation, we have a rocket book and some smart plugs. For equal equality, we have Amazon Alexa and some RGB strip lights. For renewable energy, we have an LED lamp and solar battery packs. For sustainability, we have hydro flask and self-watering planters. And finally, for our raffle prizes, we have gift cards and a Squishmallow. Wait, what's that? Raffles? Yeah, so for each workshop you attend, you actually gain 1 chance and 1 entry to participate in the raffle to win our gift cards and our Squishmallows. So yeah, there's going to be a secret code handed out at each workshop. We'll have a form at the very end. You type in all those secret codes, and each secret code you get is 1 entry into the raffle. So for our Durham side, here's our location information. So make sure that you stay in this general area. We want to have a community feeling to this kind of event, right? So make sure you stay in ETC. We have the Woolworth room, and we have the classrooms on 2nd ETC as workshop rooms. All the food is going to be in Woolworth throughout the event, and we have a bunch of tables in Woolworth, as you all know. So you can co-work there, you can talk with other teams, you can get a table for your own team and just grind away. If you do need a quiet place to get something done, we've also booked the classrooms on 2nd Bryan, so 2 floors up, and take the like the pipeline across, and you can go to any of the marked classrooms on Second Bryan, just chill out there, get some work done privately. Yeah.
So for the Morganton campus, you want to stay in the AC. Most of the building is reserved for you. And when it's time for meals like breakfast and lunch, you want to go to the cafeteria. And all of the workshops will be held in the Fab Lab. For virtual participants, the Zoom links will be on the schedule. So you can access the schedule via the emails that were sent out or through the website. So feel free to join the main session at any time. This will be the main hub, so all the workshops will be held there, as well as team formation. And we can place you in breakout rooms to meet other virtual people or to get help, or just to work with your other teams. So for submission, we will be using dev post for the platform. And so the dev post will be sent in an email shortly after this. The teams should be added to dev post, and yeah, just meet new people, make new friends.
I want to interject here real quick. So the dev post will have the rubric and like all the other information on what you actually need to submit. And keep in mind, we're gonna have like a video you need to record about presenting your thing. So make sure to check that out before you like go full on coding, so you know what to work on.
So if you need any help at any time, the main communication platform we're using is email. So if you have any questions, you can email smathhacks@ncsm.edu at any time, or you can find one of the directors, so Pratham, Ayush, or me, or any of the organizers, which some of them are sitting here, and then I don't know where they are in the Morgan campus, but. And also thanks to our generous sponsors. They helped so much in terms of the funding, and that's how we were able to give so much swag to you and just pull off this entire event. And also thank you to Mr. Dargenio, Mr. C, and a bunch of the other adults that were involved with attending this event.
Sure. And for a quick demo, okay, I'll just stand here. For a quick demonstration of the power of AI, we have a WWE style intro speech for our amazing keynote speaker. Ladies and gentlemen, brace yourself for the unstoppable force of innovation and sustainability, the Sultan of Solar, the Wizard of Wind Power himself, Steve, the sustainability savior, Lysenko, hailing from the prestigious battlegrounds of NT Clean Energy Technology Center. This master of clean energy efficiency and renewable systems is here to slam down the carbon footprint and champion a cleaner, greener future. With over 15 years of experience in the field of power generation, utilities, and renewable energy, Steve Lysenko is not just any engineer. He's the heavyweight champion of the renewable world, battling it out for our planet's future. Put your hands together for Steve Lysenko.
Big round of applause.
All right. All right. Welcome. Thank you for having me. That was quite the introduction there. I'm Steve Lysenko. I'm a mechanical engineer at the North Carolina Clean Energy Technology Center. That's part of the College of Engineering at North Carolina State University. A little later on, I'll be going through my day-to-day little brief overview of some renewable energy technologies. But before that, I wanted to get into a little background how I got into the clean energy sector. If you're my age or older, you probably didn't know that you were going to get into the clean energy sector when we were your age. There's a QR code up there for the Slido Q&A. You submit questions at the end. Hopefully I can answer those. It's on the next slide too, so we don't get it on this one. Those that pictures from like a year ago wearing the same shirt. I promise you, I own other shirts. So here is my path from Iowa to Pennsylvania to North Carolina. So I was born and raised in Dubuque, Iowa, which is right on the Mississippi River, right where Iowa, Illinois, Wisconsin all meet up. I don't have an elaborate, long-winded story of how I became a mechanical engineer. It was pretty straightforward, easy path. So the subjects I enjoyed, science and math. If you're good at something, or you're interested in something, you usually do good at it. So that's what I was interested in. That's what I did. So why mechanical engineering though? So my brother's 8 years older than me, mechanical engineer. He worked at Ford Motor Company his whole career. My father, also a mechanical engineer. So he worked at John Deere for 40 plus years before he retired a few years ago. So that was my path to mechanical engineering. I knew what kind of careers they did, what they did for a daily basis. Thought, hey, that'd be pretty interesting. I can see myself doing that. So that's where I went. So I just had to find a college, which was also a very clear, easy path there. Iowa State University had a very good engineering program, and the in-state tuition helps, especially when you're working minimum wage. Dairy Queen, Hardee's, those were minimum wage jobs for me. Actually, Shopko, do they have Shopkos? It's like a Target, Walmart. I think they're all closed down now, but 10 cents more than minimum wage, really raking it in there. So that was a good engineering program, in-state tuition, Iowa State, there I was. Around sophomore, junior year, that's when I started to deviate from footsteps of my father and my brother. The subjects I was interested in were the ones that they hated. Heat transfer, fluids, thermodynamics, those are the ones I liked. And having a little more hands-on background, restoring cars, learning how to weld at an early age, something I still like to do for hobbies. Opened up a lot of opportunities for grad school experience or grad school opportunities for research assistantships. So that's where I ended up. So ignoring scholarships, fellowships, there was 3 paths to get your master's. You either pay for it, do the classes, or you get paid for it by doing research, like maybe 20 hours a week, and then coupling that with classwork, or doing teaching in an undergrad heat transfer lab, which I did that for a semester, and then coupling that with classwork. So I did the research assistantship, which was title stuff on that, but fluidized bed gasification. All right, making hydrogen from corn or switchgrass. People don't know a lot about Iowa, but one thing people do know is there's a lot of corn there. So making hydrogen gas. So picture a fluidized bed gasifier, a big cylinder. You fill it with sand, you inject air or nitrogen or steam at the bottom of it, bubbles up, and it creates the sand in like a suspended state, a constant suspended state. So it acts more like a fluid. So a beach ball would rise to the top, softball would drop to the bottom. And you can burn corn or switchgrass in there, combust that, or you can use the heat from the sand in the absence of oxygen, process called pyrolysis, to create hydrogen. Fuel of the future, they called it back then. 20 years later, I still hear it sometimes. They're doing a lot of research, a lot of challenges, a lot of engineering challenges have been overcome in the last 20 years. Still a lot of challenges that need to be overcome. But they're doing a lot of research in it still. Just a few months ago, Department of Energy announced or awarded $7 billion for hydrogen, 7 hydrogen hubs across the nation. So, I mean, I know what $1 billion is, 1,000 million, but wow, it's a lot of money. It's hard to wrap your head around $7 billion, but a lot of research, a lot of funding still in this space. So when I was getting my master's, my professor that I was doing research under was the head of a new department called Biorenewable Resources and Technology. So that was my first introduction to biorenewable energy, renewable energy. Wasn't a requirement, but it was one of those unspoken rules that you're under him, you're majoring in a traditional, like mechanical engineering, and also in biorenewable resources and technology. So there wasn't as many opportunities back then in that field as there are today, but I knew I still wanted to stick with the clean energy sector. So I went to work at a company called PPL, which is similar to a Duke Energy Progress, Duke Energy Carolinas, but up in Pennsylvania. Most of my time, 10 plus years, was spent at a power plant, so a 1,500 megawatt power plant, equivalent to powering about 1 million homes. So if I thought that scale of my 1 megawatt thermal project in grad school was big, and it was at the time, like you had to climb up a ladder and everything, dump sand in, thought it was big at the time, but this thing is huge. So that green arrow that's pointing to a guy that looks like about an ant, that's the scale of a human being, and that's just the boiler sides. That's one part of the power plant. So gigantic size there, gigantic size. So they would say, hey, go familiarize yourself with the equipment the first couple of weeks. I don't know what I'm looking at. I've been like, getting lost. I'm just happy to get outside to get my bearings back, but a big place. A lot of engineering challenges that came along with it. So when you're getting pressure, 5.7 million pounds per hour of steam flowing through the turbine, and your pressures and temperatures are so high, 3,600 PSI. Picture your pressure in your tire on your car is like 36 psi. Picture 3,600 psi at 1,000 degrees. So in your physics classes, you probably hear your three states of matter: your solid, your liquid, your gas. Well, once you get past a critical point, which is 3,200 psi, 700 degrees, we exceeded that, you get into another state of matter called supercritical fluid. All right, you can get much more efficient power plants that way. But it comes with a lot of challenges. As a maintenance engineer, that makes it tough on the valves, the pumps, tubes, your piping, everything. Think of stuff that has to hold up to 1,000 degrees steam temperature and 3,600 psi. So there's a lot of challenges there. Make it not so doom and gloom. We're always fixing things. We call them opportunities. So a lot of opportunities existed, but they don't just happen. Something to keep in mind when you're going into your careers. Maintenance jobs like that, stuff doesn't break down just 9 to 5. You can be sure that you get out there with your friends or on a date, whatever it might be. Those are the times that the plant's calling you, hey, this broke down, you got to come in. So keep that in mind. Choosing a career path, not for everyone. The last 5 years of that went into as the plant's controls engineer. So there you're controlling, you want everything automatic. Right? There's a lot of processes that go on. Picture a tank. To control the level in the tank, you don't want to get out there turning a valve. Oh, hey, it's going low. Let's open the valve. No, you want to automate that. So picture just a tank. You want the level, so you have a level that comes back, a sensor says, hey, okay, I'm 32 feet, 6 inches. Okay, good. I'm getting a little low. So then your controls, your computer, your control system, your distributed control system, it's like a PLC, then says, okay, I'm going to send a signal out to the valve and control that, either electric or pneumatic, using air. Maybe you want some feedback to make sure that that valve's doing what it can or what it should be doing. So there's 3 signals. Out of the plant, you had 10,000 signals going in and out all at the same time, controlling that, all working in unison. And it only takes one of those to get out of whack, to throw everything out, shut down the plant. So a lot of opportunities there too. But I was down in 2012, I was down in Greensboro, Center for Creator Leadership. Had some management training. Spent the weekend in Raleigh, just fell in love with it, and made a couple more trips, and that's what brought me down to Raleigh. So when I got down here, then I got a job at North Carolina State University. Still with them now, but in a different role, different department. I was the plant engineer on campus there. So that's the kind of behind the scenes. So instead of having every building have its own chiller and boiler to heat and cool the buildings, you had one separated. So you got science and math. Good chance you'll be on Centennial campus, highlighted in purple. So instead of having every one building have its own separate system, you had one building, a lot bigger boilers. We had its own turbine, so generate 25 to 75% of the power right there on campus. Take that exhaust heat, instead of just sending that up to the air, use that to create steam. Maybe heat some buildings, send it over to greenhouses on campus. College of Textiles, they use a lot of steam for their processes. So out of the plant, focused on reliability, you shut down, it's a financial loss, huge financial loss, but still there's another plant that'll pick it up. And so that you as a house, your house still has power. You don't even notice that the power plant went down. Out of the campus, different story. Now you're focused on redundancy, resiliency. So if a boiler goes down, do I got another one? How quick can I get it up? You can imagine the impact since it's all centralized at one plant. If every building on Centennial campus during finals week in December at 50-degree temperatures, you can imagine how many phone calls I would have been getting at that time, looking for a new job. So still with North Carolina State University, but I'm at the Clean Energy Technology Center right now. It's part of the College of Engineering there, and it's been around for 35 years. If you've been to the solar house, spun off of that, the Solar Center, it used to be called, and do a lot more than just solar PV now. That's why the name changed. Do a lot of different areas. So I'm in the clean energy and energy efficiency group. There's a transportation group. There's a training group. There's a policy group and a communications team. Quick plug for the policy team, Desire It. If you've heard of this database, it's pretty neat. You type in your zip code, it's free to use, whether you're a homeowner looking for a heat pump or whether you're an industrial client looking to put a lot of solar PV on the rooftop, type in your zip code, tell you what kind of renewable incentives, rebates, ways to help you pay for that are out there. It's free to use. A lot of very well known in this space. Approximately 1 million unique users go there every year. So, but back to what I do. So, get a lot of federal funding from Department of Energy, the DOE, USDA, United States Department of Agriculture, EPA, Environmental Protection Agency. Pretty much looking whether you're a rural small business, a farmer, an ag producer, industrial client, a high energy user, whatever your case may be, to look at different renewable energy technologies, see what's the best fit, size it, tell you what the costs are, the savings, and what your greenhouse gas emission reductions will be. That's in a general. So going to go over a little bit broad overview on a lot of renewable energy technologies that I work with. Hopefully it doesn't feel like a classroom here, but so hopefully so just some fun facts, maybe inspire some projects for the weekend. So starting out with solar PV. Solar PV has been around for a long time. Einstein was writing papers about it at the turn of this 20th century, like 1905. 1954, they invented the first, what we would call solar PV cell. Still operates off the same principle. A little bit, it's more efficient now. It's like 4% efficient then. Now it's over 20%. It was on satellites back in 1958. Vanguard 1 had it on satellites, and it was orbiting around working for, I think it's like 6-8 years to power their radios. So it's been around a long time. So why now is it just starting to become more? Well, the cost of manufacturing is coming down. So the cost of it's coming down. They're getting more efficient. And day by day, everybody's caring a little bit more about the environment. Bringing up to speed, a quick overview of solar PV. So what you see on the rooftop of a house, that is your solar array. Everything you see up there, that's an array made up of a lot of modules. Some people call them panels, but they're modules. And within those, you have the cells. All right. The cells are made from ingots that just a cylinder, and they shave off, make a lot of wafers. So you have a lot of circular little wafers. Those circles, they cut off the tops, the sides, kind of make them squares, but they still have rounded edges. You can fit more onto a module that way. And there might be some people that like the look, but most people don't want a polka dotted, looking roof. So that is why they're manufactured. That's just one way, the monocrystallines. There's other types, but that's the predominant one. Take the solar array, it goes through the inverter, takes that DC energy, converts into AC energy, what your home uses, what the grid is. So inverter, when I was starting to get into solar PV, the very first thing that hung me up was the inverter. Okay, an inverter, it takes DC to AC. It does a lot more than that. But regardless, it's still called an inverter. So it optimizes the power that comes out of the solar panels. It can sense grid outages and shut down. So for safety reasons. So another misconception. So if you see solar PV on your neighbor's house and the grid's down, you're like, oh, I'll go watch TV, play video games with them. No, they probably don't have power either. And it's just for the same reason like a generator. If you think that the grid is de-energized, you don't want to inject power there. So people think it's de-energized and safe to work on, and then you're back feeding it. So it actually shut down. So those do not have power as well. Now you can couple it, you can get a hybrid or a multi-mode inverter, couple that with some battery, and then even that does more than just DC to AC. It can go rectifying AC to DC. Still called an inverter. No matter what, it's still called an inverter. So just keep that in mind. It does a lot more than just convert. Tilt and direction. I hear this a lot too, like, well, my roof's not right. I don't face quite south. So everybody knows that the sun rises in the east, sets in the west, but the path changes throughout the year. So in the summer, you're higher up in the sky, following that red dotted line. In the winter, you're lower, down at the blue line. So your tilt, so if you just had one tilt, where do you face it? Facing the summer, so it's getting the optimum power from the summer. Winter, now you're probably right in between there. That green spring fall line is the ideal spot for it. So here in Durham, out in Morganton, anywhere where you go, you line it up to your latitude. Just coincidentally enough, just your latitude. So 36 degrees latitude here out in Morganton, that's where you line it up. That's where your optimum power is. But it doesn't matter all that much. I guess that's the point of this one, you see over there on the red, the slope of the roof, you're still getting over 92% of the power. Where it faces, and then you're like, oh, my roof doesn't face directly south, maybe southeast, southwest. Once again, even if it's at a 45 facing like southwest, you're getting 94% of that power. So what do? You put it on the south something roof, don't care about the slope, put it up there so it looks nice, and you're getting over 90% of that maximum yield. So what I do, part of the solar PV assessments, I use a software called Helioscope. There's a lot of commercially available software packages, but it has satellite images, can do 3D modeling. You can, like on the left, you put panels on the rooftops. You can put it out in the field. You can draw trees on there that has the shading effect. And then it'll tell you how much generation, your monthly generation, that it'll produce AC energy. So you can see how much money you'll save on your bills, how much greenhouse gas emissions that you'll save by producing energy this way as opposed to getting it from the grid. The top right one was one I modeled for UNC Greensboro. So if you've been there, well, hopefully not this building, that's the campus police building there. We modeled it for them. So that's paid software though. What's a free software, which might be neat for you, is PV Watts. So NREL, National Renewable Energy Laboratory, website's at the bottom. This is free software, free internet. You go on there, you don't have to register. You type in your address, like I did here. Here's your Bryan Hall. You draw a rectangular box there in the red. You see that? I'll tell you, okay, on that roof, 19.5 kW of DC. That's the solar array size that you put up there. There's your monthly production for your AC energy. Pretty neat tool. Check it out. Like I said, you don't register. You're really concerned, put in your neighbor's address. Agrivoltaics. Here's one that's picking up steam. So a major criticism, or one of the biggest criticisms for putting a lot of solar on farmland is you're taking that farmland out of production. So here's a compromise between the two of those. So as you see in the middle, you raise up the panels. Underneath it, still grow crops. Or you can have pollinator-friendly vegetation, like for butterflies, bees that help out the crops nearby. Or you can graze sheep. That would be the advice. You can graze anything, but cows are a little bit too big. They're big and they itch off scratch themselves and ruin the equipment there. And goats jump. So sheep are the preferred grazers for agrivoltaics. Wind energy. You don't hear too much about it, except for maybe on the coast in North Carolina. And there's a reason for that. So the map on the left, you see the colored areas. That's where you have the most natural wind resources that make it kind of economically feasible, that competing with other like solar PV or traditional fossil fuels. So I haven't done really assessments in North Carolina, some for clients in Texas and other places that you see here that have good wind energy. There's policies that dictate how much wind power will get deployed, but you still need that natural wind resource. So out west, like out in the mountains there, maybe some out there and on the coast. So that's pretty much for North Carolina is where you'll see wind energy. Heat pumps, you might be familiar with heat pumps. We look at these as well as an option there. It's a lot more efficient to transfer heat from one place to the other than it is to generate it. It'd be like 6 times more efficient to transfer it rather than generate it from like a traditional burning natural gas in a furnace. So whether it's an air source heat pump, a ground source heat pump, industrial heat pump where you're taking a waste stream, very efficient process. Geothermal, that's where you get it into the ground there, like that middle picture. Take advantage of those stable temperatures, more efficient. Because once you get down like 30 feet underground, that temperature stays the same year round. And it's about your mean temperature, air temperature that you have. So you're in Durham, maybe 60 degrees, maybe a little cooler out in Morganton. But go down 30 feet, 60 degrees, January, July, it's always there. So in the summer, it's going to be cooler, so you can cool your house with it. In the winter, at 60 degrees, it's going to be warmer. Start heating the house. Very efficient. Anaerobic digestion, not the most glamorous one here. Taking the pig and swine and food waste, whatever it be, taking that methane, cleaning it up, using it kind of like natural gas. All right. You can use it in fuel cells, reciprocating engines, generate power instead of just having that methane as a greenhouse gas be emitted into the atmosphere. Why is it important in North Carolina, though? There's 10.5 million people in North Carolina. Anyone want to venture to guess how many pigs or hogs are in the state? No guesses? All right. About a 1-to-1. Not quite a 1-to-1, but there's like over 8 million pigs or hogs in the state. A lot. So that's why I bring this up in the slide, even though it's not it's microgrids. Department of Energy, we have one grant looking at like Wilmington, who's prone to flooding, or out on the coast where they're prone to storms. And picture the grid going down. You don't have the power. Flip that switch. Now you're independent. You have your distributed energy resources like your solar, your wind, your battery storage, so that if your grid does go down, you can weather that storm for a few days. Maybe a community center everybody can gather at, fire station, police stations, for town safety, maybe a grocery store so you can still get food. So there's your tracks. Talked a lot about the renewable energy, which trickles over to resource conservation, sustainability. One thing I didn't talk about was energy efficiency. So that the cleanest energy you have, cleaner than any technology I talked about so far, energy efficient, the power that you don't use. So that's whether you want to go over to LEDs, variable frequency, there's a whole sector. There's companies that that's all they do is go into places, businesses that say, hey, how can we reduce your energy consumption? How can we make your energy more efficient so you're reducing it? And then with whatever you got left, then do some renewable energy with it. It's a separate track here, equal equality, and that's good. Draw some much needed importance and emphasis on it. But that's bringing everybody along with you. Not leaving out any members of society, bringing everybody along with, so that everybody can benefit cleaner environment. It's a separate track here. I'd encourage you to think about it in the next, over every track that you do, over any project. If you're asking yourself these three basic questions, who are you helping? Who are you hurting? Who are you leaving behind? You're asking yourself those three questions, probably on track to be responsible with that equal quality. So I'm excited to see what you guys are going to do for your projects over the weekend. Even more excited to see what you guys will be doing over the next 20, 30 years. There's a lot of opportunities, a lot of funding in clean energy. So maybe I'll see you in this industry with me. You'd end up going to NC State. We do hire interns at our center too, so keep us in mind there too. There's a little plug. And open it up for some questions. The QR code's on there. But if there's no questions, once again, thanks for having me.
So on the different side, So on the Durham side, feel free to raise your hand, ask questions in person. I'll be reading out loud. Let me make sure the mic can get me. I'll be reading out loud any questions that you submit to the QR code online. So scan that QR code, just submit your question. I'll read it out loud here. But if you have any questions on the Durham side, raise your hand.
Yeah.
So I think it's the clean energy side of the system. Do you guys ever collaborate with the climate change center?
The Climate Change Center out of so all the different departments, yeah, we get involved in. So we as a center have a lot of different groups, whether it's the policy, transportation team. So we work with sustainability clubs, clean energy, climate change, professors on campus, a bunch of different ones. Yeah, so hopefully we don't get isolated just in our little center there, but we're trying to work with as many groups. And yeah, are you involved with them? I got you. Yeah, I've heard the name. I haven't personally worked with them on any specific projects, but I know people in our center have.
What are your thoughts on nuclear fusion generators for clean energy production?
Yeah, so renewable energy, that nuclear used to be kind of in a separate discussion. So you used to have like the solar, the wind, that was all in one box. and then you had the nuclear and another one. They used to be separate. They're starting to become all together there. And I would say that we should look at all available technologies that can reduce your greenhouse gas emissions, your carbon footprint. Look at it all. I think it's a viable technology, and I think we should look at everything.
As students preparing for college, what sort of things do you recommend getting involved in?
As far as getting involved in, find something that you're passionate about. I would. 30 years is a long career to find something that you're not going to be passionate about. So start finding some activities, clubs, anything. The more you're engaged in it, then you can find out whether, hey, is this really something I want to be involved in for the rest of my life here. So that's just in general. So advice I give. Yeah.
So those like energy production, like how much shit actually costs? Is it are those things that's more sustainable? Smaller ones?
So the energy efficiency, yeah. So simple cycle ones will be the most. So oil is going to be, if a plant's burning oil, which most of them are phased out, those would be the highest emitters. Then you have coal; those are all shutting down and getting converted to natural gas, most of them. And then within those, you have simple cycles, meaning you just burning the fossil fuel and converting that to electricity. But then you can have combined cycle cogeneration, like at NC State, where you have that exhaust heat and now you're creating steam from it. So now you're almost like doubling your efficiency. All right. Same thing out there. So you can have a steam turbine. So through there, it goes through your natural, spinning the turbine, and then you have another turbine. So you have like a natural gas power in one turbine, and then you have the excess heat or the steam power in another turbine. So that's when you get the efficiencies up there more. So it's really what fuel you're using, and then the bigger the scale, the more efficient you can be just on scale. But within that, you want to get it the most efficient technology. That's answering your question there.
I was just wondering, like, if you have like small scale generators that tend to be like kind of less renewables and stuff. I think they generate just like
Yeah, so I mean, if you're saying you have one generator that's powering like 1 million homes rather than 10 that are powering 100,000 each, is that what you like? That one is going to be probably more efficient if you have just one. But that's if you're assuming that same technology and you're scaling it up. You can get into different technologies, and then you can get into areas where maybe you're using some other fuel that's you can source locally because you still have to transport. So it gets a little bit more trickier than that I can give a real quick, clear answer for. But if it's just the same technology, it's going to be better if it's scaled up. But then you can get a lot of different technologies if you kind of distribute out your resources, and then you can kind of mix in different ones like solar, wind, to get into that generation portfolio. Yeah. Of free modeling software?
thinking like a way for Keynote design. Is there any like software that you think that's good for that?
Yeah, so there's a couple softwares. Reopt, REOPT, is a free software that you could use. That's from NREL, National Renewable Energy Laboratory. SAM, System Advisory Model, is another one. And I don't know how long it'd take you to catch up to speed on these free softwares, but you check them out, at least the basics. PV Watts for the solar PV. Those would be the three resources that I can think of off the top of my head that are free for the public, that have some of that modeling capability in it.
What technology gives you the most hope for the future of our environment and society?
Oh, geez. That's a hard one because I don't want to pick. It's kind of technology agnostic. Meaning we're not picking a favorite. I think we got to look at all of them, whether it's solar, wind, and I think it's going to be a combination of all that. Combination of, there's not going to be one clear, hey, this is going to be the one technology that gets us through it. I think we have to look at all technologies, and eventually they'll make some technology breakthroughs. It happens with everyone that says, oh, okay, now this one's winning. And then once you just think that that one's going to be the one, something else comes along, they make that more efficient. I think it's good to have all these different ones, as long as we're getting there, and we're getting close, almost there, that they're competing with traditional fossil fuels for costs.
What do you think about the new research into vertical double-sided solar?
So I don't know the new research. So the bifacial, yeah, constantly. That's what I was talking about. So the panels that you see on people's houses 20 years ago aren't the same as what they are today. They won't be the same 20 years from now. So bifacial, yeah. Right now the cost they're kind of newer, so the cost is still up. But anything to make them more efficient, and that goes with that agrivoltaic. If you saw the one picture on the right-hand side, the vertical one. So instead of having them facing south, you have them face east and west. And then you can grow a lot more crops with them too for the multi-purpose, and they're efficient. Yeah, so anything people can do to make them more efficient. And those are those engineering challenges, and still a lot of research that can go into solar PV. So it's not just stuck on, hey, this is solar PV right now. There's so many innovations that can go on, and that's one of them.
Where can AI help in their own clean energy?
Yeah, AI, put in a new one. Top of my head real quick, I would say predicting weather forecasts, dispatching power in that space. If you get a better handle of how much load's coming, then you can shed load, distribute energy, like with the microgrids, or what they call virtual power plants now. That's where I would think that AI could benefit from the most.
How do you build, or is there a certain way to build the heat systems?
Say that again?
This was how do you build, or is there a certain way to build the heat systems?
So I'm not sure like what specific like by heat systems. If you're talking power generation, like combined heat power or any solar, anything, we look at their electricity bills first. So you see their peak loads, because you can't have solar exceeding what their peak demands are. You got to make sure, and if it's a combined heat and power application where you're using like electricity, then you're using the byproduct, the waste heat to generate steam that you would usually use natural gas for, you got to make sure that those loads are. So you would look at their heating loads like natural gas bills, electric bills, and start sizing it from there.
Seems to be the last question, and I guess this has already been somewhat answered, but what do you think the main method of power generation will be?
20 years, yeah. I think it's going to be a mix of every technology that I've talked about, and probably some that I didn't even touch on.
Any last questions here on the parent side?
Yeah.
So I want to talk about some companies who come in and help businesses like work on their energy efficiency in places like metropolitan areas. What kind of energy tech would you recommend for those people? Like when there's like a high amount of people coming into these businesses, there are places that are like have high volumes of people populate the area. It's kind of hard to put like solar panels on like cities like apartments and stuff like that.
Yeah. So for those ones, just start with the energy efficiency. So the easy ones that they go LED lighting instead of just incandescent bulbs that give off heat and light. Pick something that just gives off light. That's the number one. Variable frequency drives. So you get affinity laws. Basically, instead of having a motor run at 100%, you knock it down to 90%. You're not just reducing that energy by 10%. It's a cube factor. So it's 0.9 times 0.9 times 0.9. And that's your energy that you're using. So you reduce it down. So drives like that, you could have heat pumps. Heat pumps would be another one. Really, you look at their individual. That's why those companies exist, that they go in there and they do the audit. They do the walkthrough. They look at all the HVAC equipment. They look at all the equipment that exists, look at their building envelope specifically, and then figure out, hey, these are going to be the biggest bang for the buck. As energy efficiency measures is what they call them, and what's going to give you the best payback. So then the company would be like, oh, okay, that doesn't cost that much. Even smart thermostats. There's a lot of companies that don't even control like the room temperatures, come in there in the morning, ramp it up on the way out, maybe forget about it. Even smart thermostats. So there's it just depends on what business. And that's why there's companies that exist that have a whole staff of engineers that just go into these buildings and assess them. No? All right. Well, appreciate it again. Thanks for having me.